Okay, thanks for reminding. So the specification, so the resistance has to be in ohms only, and this value we have to give to the manufacturer because we are the one who are doing this calculation. Okay, and this will not, this ohmic value when you do the calculation, no, it will be like not in micro ohm, not in kilo ohms. Okay, because this is resistance is connected in the secondary of the transformer. So it will come something like 1 ohm, 2 ohm, 3 ohm, like that. Okay. And then the voltage, actually, the voltage here, in this case, the voltage will be how much? It will be 220, 230 or 240 volts. So we'll take a low voltage, LV resistor. Okay, if you take LV resistor, then our first thing we should better not specify non-standard voltages also. Cost will go up. So low voltage 220, 230, 240 means it is LV. So we specify that. Okay. Here insulation level for LV means it is that same, no? 1 kV, 1 minute.
Yes, 1.1 kV.
1.1 kV. So whatever is applicable for LV will be applicable here. And what is the insulation level, LV?
1.1 kV. Sir.
Okay. This 2.5 kV is for what?
2.5 kV. No, sir, I have not come across this thing. For 415 volt, we specify 1.1 kV.
Okay.
Till 415.
Okay. And frequency 50 or 60 hertz. Actually, frequency also plays very important because what happens, the AC resistance and DC resistance are different due to the skin effect. So almost you can say 20%, 30% resistance value will change if the frequency is different. So if you are doing some North American project and all, you are specifying 60 hertz. But if we are working on, let's say, 2-3 projects simultaneously, one Indian project and one foreign project, you have to be very careful about frequency. Sometimes project may be North American project, but the NGR, they may be planning to put it in, let's say, UAE or Oman.
Right.
So you have to be careful. You have to see where is the final installation going to be there. Okay. And then coming to the current rating, this continuous current rating, yesterday I've explained, you know, don't give this continuous current rating. Let us give the short time rating itself. And when you give the short time rating, give the actual current in amps. For example, 2 amps, 3 amp. See, NGR rating will be in amps. NGT rating will be in kVA. And you can also give how many, see, second you can give, because this is very important. The fact when they are doing, they will do for this particular time only. So specify the time also. And this time, as I told you yesterday, you please follow whatever is the practice of the owner. If you are doing a project for some NTPC or NHPC, whoever is the owner, you check their standard and follow that. If they say we don't have standard, you give 1 minute. Okay, don't give don't give 30 minutes. All those, that is too high. See, this temperature rise, actually, this is basically for the test. That resistor, when you continuously send the current, the temperature should not increase 385 degree. And similarly, if you apply for short time for 10 minutes, it should not increase 760. But actually, if you see, in the when you apply NGR for low resistance neutral grounding, this temperature rise plays very important role, because there the current was like 250 amps, 400 amps, 300 amps, right? So 250 amps square into R will give so much amount of joules, right? Now here the current is 2 amps or 3 amps. So 2 amps square the resistance will not give so much amount of heat. So in case of only NGR, the amount of heat generated is very high. In case of NGR with NGT, the amount of heat generation is not so high. Okay. So that is one thing. And ambient temperature you have to specify as per the site. Then degree of protection, last time also I had told, this ingress protection you please select based on outdoor or indoor. Outdoor you can go for higher values, indoor go for lower values. Okay. And don't give indoor and very high degree of ingress protection, then unnecessarily cooling will become headache. Actually, see here you are having NGR and NGT both located in the same box. I will show you some of the pictures, or sometime there may be a small barrier like that. So cooling here, so compared to only NGR, it is not so much concern here, because amount of heat generated is less. But even then, we have to consider the ingress protection as per the site. So don't use IP55 and all for indoor. If some because see what happens is when you have NGR with NGT, you're having a big power plant. Okay, now where do you feel this NGR NGT will come in the first place?
In power plant generator.
Okay, now power plant generator, you have seen the layout of this generator room, all those layouts.
I've never worked on power plant.
You can check any of the layout.
Okay. It will be close to the generator, correct, sir?
Yes. The
Indoor.
generator, that room is there, no? Actually,
Yeah.
that itself is 2-3 tier. Turbine will be at one floor. Generator will be at one floor. So if you see that, the NGR we cannot be outdoor.
Yes.
So it will be indoor only. So because of that, don't use a high ingress protection. I think if you use IP23, it is good enough. And one more thing, the connection from the generator terminal box, neutral terminal box, to this one, what is it, NGR, NGT. How do you think they do the connection?
Through cable?
No, they don't do using cable. Actually, they are doing using the same bus duct itself.
Okay.
Because entire assembly they are doing in bus duct, no? So they are made, see actually generator face side and all is connected to bus duct to the unit transformer. Then bus duct will have a tap off. The tap off will go to unit auxiliary transformer. And at the neutral side of the bus duct, at the neutral, actually see what happened. Generator neutral side actually is not one conductor like transformer. It is actually you have 3 terminal RYB at the top, RYB at the bottom. The top RYB I am connecting to the face bus duct. The bottom RYB first it has to be connected to each other, no, to form the neutral.
Yes.
So that is done, and then from there it is connected to the NGR/NGT via the bus duct. So bus duct length also cannot be too big. Okay. Have you seen that isolated phase bus duct?
Yes, sir. Yesterday I saw in that picture, sir. I googled it and
Okay, so you can actually check IPPD neutral connection, generator neutral connection. You can see, and if I get, actually, I have seen many of them. I didn't add them here because I will have to check with the vendor. I will check with the vendors and I will try to share it with you. Okay. So, and one more thing is that length also should be less because resistance should not be high. Okay. Then. Okay, in this case, since it is located indoor, the surrounding atmosphere is not such a big concern. Then the enclosure material, we will use our galvanized steel. Okay, and mounting, this is mounted on the floor only because the weight will be more, maybe some 100 or 200 kilos. So it is floor mounted. Okay. And anything that involves short circuit, any fault current, the foundation has to be very firm because what happened, see here actually the current is limited, so that is not a problem. But when something carries a fault current and if current is not limited, there can be huge short circuit force. Okay. So here it is okay, but still we have to have floor mounting. Then
and
yeah,
this DCT is grounded to the same grounding grid of the power plant, right, sir?
actually what they do, they will connect it to a dedicated earth pit,
Okay.
and that earth pit they are actually interconnecting it with your main grid. Okay.
So, and the body of the generator also will be separately grounded to the same grid.
See, the body of the generator is connected again to the same earth grid. See, above earth, they all are isolated. Below earth,
Everything is
they are all common. Actually, there are some drawings. If you particularly see the layout drawing, no, of power plant, there you can see the NGR, NGT, they are connecting it to dedicated earth pits, and that the earth grid, and that one is interconnected with this. Actually, there is a standard also on generator grounding. Are you aware about that?
No, sir. I'll have to read about this one.
But generator grounding, one particular standard is there. I'm not able to recall now. I will share it with you, the number of the standard. Then you can see that. And if I get any layout or a drawing showing the connection from the generator neutral to the dedicated pit, I will share that also with you. Okay. And the duration, as I told yesterday, we can keep 1 minute. But if owner is giving 30 minutes, you can use it as it is. So this IEEE 32, no? This one is the standard for the NGR NGT. And I think 92 is related to most probably the generator grounding, I think. You can check once again. And the C gray 397, this is again for the neutral grounding only. And IEC 76 is that earthing, EMC, all those is there, no? That's standard. And 3151, I'm not able to recall now. OISD is mainly for mines. and oil industry. Okay. So this, do you can check the standards once.
Yeah, I will check it.
Yeah. Because I have actually in the end also I will show you, I have whatever standards I have referred, I have put there. So you can also read them. And as I told you, termination cable or bus duct is there, but normally bus duct only is used. Because as I told you, we have to do the connection, and bus duct is in a power plant, they rely more on bus duct rather than cable. Because we have to put CT also, not the new. If you see big generator, we need a lot of CTs in the neutral for differential relaying and all. So that CT, okay, we can have bushing CT in the generator also, but problem is bushing CT is put by the generator manufacturer.
OEM.
Yeah, and sometime I may not be able to specify that. So I will go for CT in the neutral of the IPBD also. That is also fine. And the resistive element, it can be, as I told you yesterday, it can be grid, a coil, plate, stamp. Basically, it can be a coil or stamping. Last time I've shown you the picture, I think.
Yes, yes.
Then material, don't use normal stainless steel, use special alloy. Okay, and let it be decided by the vendor. Now, this current transformer, why we have to use current transformer is actually not for the, you know, this, okay, current transformer you can use, but this relay will not work on current. Okay. And one more thing is, see, if you are using only NGR, you can use some special relay which will monitor the healthiness of NGR. But if you are using NGR with NGT, you cannot use any monitoring relay for the NGR. Okay, please keep that in mind, because those relays work on the concept of injecting current, and because your NGT winding comes into picture, whatever current you inject, it will come back through the winding. So you cannot detect open circuit so easily. So those monitoring relays will not work here. Then space heater, as you know, is required because we may not be using this for a very long time. So moisture should not condense. And if moisture takes place, there can be corrosion. And some people are giving a disconnector also, that is for maintenance and so on. It is not a switch, it may be a link form also. Okay. If we actually, why should we disconnect the NGR?
Only for maintenance, sir.
So see one thing, if I have to disconnect the NGR, my complete generator has to be shut down.
Yes, yes.
And when my complete generator is shut down, and when there is no voltage, see, after you have worked on power plant generator, like
Yes.
let's say they trip the generator. Suppose I want to do maintenance of the generator winding. So if I have
Yes.
stopped the generator, how many hours they will live before they start the maintenance?
Generally, for this 2.5 MVA transformer, what we did was we had a period of 15 minutes, and then we would discharge the winding and then open the neutral link.
Okay, how you did the discharge the winding?
We had this equipment for that one, where you ground the generator winding terminals.
Okay.
So we disconnect the field, we disconnect the neutral link, then we ground the uh, winding terminals, and then we work on the generator to discharge all the capacitive effect of the winding.
Okay, the stored energy.
Yes, sir.
Okay, so you're using a neutral is a disconnector, breaker, isolator, or link. What is it?
It is a manual switch, sir.
Manual switch. Okay, okay, fine.
Because it was on low voltage. It is sorry, it is 11 kV generator.
Okay,
What we have is manual switch with a lotto provision, lock of tagger.
okay, okay, fine. So in a power plant also they will have a disconnector for this isolator. Same concept. Okay. So now coming to the type of cooling. Cooling is natural only, and there is no fan. And the resistors, when they design, they will have some parallel path. Now coming to the rating of NGT. NGT rating yesterday. See, for NGT we have to make one more data sheet. Just like our distribution transformer data sheet, no?
Yes.
But not as exhaustive as that, but some values will be there. Okay.
Yeah.
So on a KVA rating we have to mention, and type of transformer,
It will
the
be a small dry type only, right, sir?
yeah, it is a small tri type transformer only, some 20 kVA, 30 kVA or something like that. But that also needs a data sheet, simple data sheet. Then now we go to the typical calculation of this NGR and NGT. Okay. If you are having your calculator, you can take it. So let us start doing the calculation. So my suggestion to you is, okay, now don't see the answer. You can start. I will guide you how to do. First, take this voltage of the generator, 13.8 kV. Okay.
Okay.
50 hertz, 70 megawatt generator. Capacitance value they have given 0.24 microfarad. Okay.
50
Now you
hertz.
okay. Now you just take a paper.
Yeah.
I will tell you what to take down. Don't see the. Then you do the calculation on your own. Okay. You write down the voltage of rating of the generator 13.8 kV.
Okay.
Power rating you write down 70 megawatt. Frequency you write down as 50 hertz. Write down the capacitance CS 0.24 microfarad. Then you wrote down this much.
Yes, sir.
Then write down the formula for XC as 1 by 2 pi FC. Okay. Then you write down the resistance Rn formula as XC by 3. Okay.
Yeah.
Then you write down NGT primary voltage is equal to V line to line by root 3 into 1.3. Okay.
Okay.
Then you write down turns ratio and just leave it blank. You have to calculate that. Then you write down Rn is equal to you write down Rn primary divided by turns ratio square. Okay. Then you wait. Okay. For current density short rating is equal to. Then you write down resistive component of current is equal to V phase by Rn primary.
Yes, by Rn prime.
Okay. Then you write down NGT short time rating, KVA rating is equal to V phase into resistive component of current. Okay. Okay. Now you don't see this slide.
Yeah.
Okay. Whatever you have written down, no. For that, you please start. You do the calculation. You take 5 minutes and do the calculation. So any doubt?
No, sir, I will do it.
Okay. Okay. Please do. So you got any value for
XC, I got 13270
okay 13270 ohms, right?
ohms. Yes.
That is almost like you can say 13 kilo ohms.
13 kilo. Yes, sir.
Have you done the mega test and all for insulation?
For cables, yes, sir.
How much value you got?
2 mega ohms.
2 mega.
Sometime.
You can see here actually is almost like 10% is the this one. Okay. But there what you are getting is R. Remember that
Yes.
one.
Yes.
And there it is not X. It is only R value.
Correct.
What Megger is giving. That is why normally in Megger also sometimes they are waiting, because immediately when you do the connection, the first few seconds whatever you are getting, the capacitive effect also will come into effect. So later on it is only the resistance. So have you seen anything in that Megger manual, that one?
Oh, I have to check
You
that.
can once again check something like that is there. Okay. So, okay, we got the capacitive reactance as 13 kilo ohms. So, how much you got RN?
4423.
44. So, you know why RN is XC by 3. Yesterday, I showed you from the symmetric component, right?
Yes.
Yeah. Then, what is the voltage you chosen for NGT secondary?
NGT secondary will be 220 volt.
Okay, you have also taken 220 volt. Okay. Then what is the primary voltage you took?
Primary 8.26 kV.
Okay, that is 13.8 by root 3 into 1.3, right?
Yes, yes.
Okay. You can also take 11 kV also. Okay,
Yeah.
sometimes that is also allowed. Then how much you got turns ratio?
Turns ratio I have not calculated. So turns ratio. Uh, 37.
You got how much? 47.
37.
37, huh?
Now, how much is there? Yeah, because I made 8.2 kV.
No,
And
13.8 by root 3 is how much?
13.8 by root 3 is into 1.3 is 8.26 kV.
Please check once again. 13.
So 13.8 is it?
8 divided by root 3.
No, sir, I took 11 kV.
No, no, not 11. It is 13.8
Yeah,
by root 3.
it is 10.36 kV.
10 point?
36 kV.
Okay, so you take that only. So you can choose 11 kV, make it standard. Choose the primary
Okay.
voltage, set it as 11 kV.
So I get 50 now.
You got 50.
Turns rate.
So now your 13 kilo ohms was your resistance, and the what the actually the neutral sees, right? But what is that? But the resistor, when we connect in the transformer other side, we don't need such a high value. So it will
Right.
be how much? 13 kilo ohms divided by 50 square.
Yes. $5.3.
Okay. Sorry, it is not X. It is RN. You determine RN of 4420.
4420.
Because we are calculating the RN value, right?
1.76.
Yeah. Because RN in the secondary is 4 kilo ohms. RN at 11 kV side is 4 kilo ohms. RN at 220 volt side is 1.76 ohms, right?
Yes, correct.
So now, yesterday you saw that symmetric component, no? I showed you the zero, positive, negative sequence network connected in series. There in the positive network, you saw the voltage, right? So the fault current I told you was the resistive component was V divided by V phase divided by Rn, right?
Rn is that in the primary.
Yeah.
Resistive components V phase divided by Rn.
The phase voltage of the system you take now. Okay. Don't take the voltage of the transformer primary. Sometimes for standardization purpose, you may take some other voltage. Don't take that one. Take the actual voltage of the this one generator.
1.8 resistive.
Can you check once again? It is what is the voltage you took? Phase voltage
13.8.
13,800 divided by root 3.
Yes.
And what is
And
the
that divided by Rm.
Rn? How much you took?
4423.
442. So how much amps you got?
I got 1.801.
Okay, 1.8 amps is the fault current that actually. Now, actually, what is the fault current that actually flows in the generator winding? Can you tell me what is the fault current that actually flows in generator winding?
Yeah, it will be 1.8 amps.
No, this is actually, see, yesterday, this is the, when a fault takes place inside the winding, you saw one slide, no? One current going to left, one current going to side, right side.
Yes.
You remember that slide?
Yes, sir.
So that left one was the resistive part, right one was the capacitive part. And actually, in the entire concept of this is resistive component of the current and capacitive have to be equal, right?
Right, correct, correct. So it
And
will be less than
capacitive
this one
current we
capacity.
cannot stop; it will be there.
Right.
So this you know that resistive and capacitive current are always 90-degree, right?
Out of phase.
Yeah. So you take into root 2, you will get the fault current.
Into root 2, sir.
Yeah, yeah, because the two items equal. A square plus A square is 2A square. 2A square, it is the hypotenuse, no? 2A square, if you take the square root, is root 2A. You understood? The, normally, if, capacitive current is in the y-axis. Resistive
Yes.
current is in the x-axis. So that
Yeah.
is like a triangle. If you take the hypotenuse, is the resultant current. So the hypotenuse
Root
is
of C square plus R square.
so R and both the current are equal. That's why it will be root 2 times A. That's why root 2. So fault current will come how much? 2.5 amps is the total fault current, right?
2.55 amps.
Fault current we are not giving to anybody, just for your
So this will include resistive and capacitive.
yeah, for the fault current, but for the NGR or NGT manufacturer, for the specification for the data
Only
sheet,
resistance component.
this fault current will not come into picture. This is only for your understanding. I have told. So now you multiply this 1.8 amps is the resistive current you got, right?
Yeah.
Now what will be the that 1.8 amps is the current in the
Primary side.
generator side, or the transformer 11 kV side. So what will
Mhm.
be the current actually flowing through the resistor?
On the secondary side,
Yeah,
into turns ratio,
multiply by the turns ratio. How much you got?
90 amps.
90 amps, right?
Yeah.
Okay. So now kVA rating is nothing but voltage into current. So you can take either secondary voltage into secondary current, or you can take primary voltage into primary current. Primary voltage is how much? 11 kV you have chosen, right?
11 kV into 1.8.
Yeah. So how much you get?
19.8 kV.
Okay, you multiply 220 volts by 90 amps. Take how much you're getting?
The same, sir.
Same.
19.8.
So the kVA rating is out like approximately I can say 20 kVA transformer rated for how much? What is the short duration you are going to take?
1 minute.
Okay, so you want 20 kVA transformer for 1 minute, right?
1 minute.
You will
Yes.
take dry or oil.
Dry.
Okay, so you want a dry type transformer 20 kVA for 1 minute. Now that
Yes.
actually with the vendor is giving, he is actually it will not be a 20 kVA transformer. It may be 5 kVA or 10 kVA something. He will decide it. Okay.
Yeah.
So let us not think about that one. And what is the resistance value you got? Ohms R NGR resistor. What is the ohmic value of NGR? How much ohms you got NGR resistor? You are able to make out how much ohms you got?
1.8 is the fault current.
1
Secondary
point
side, I'm getting 1.8, sir.
1.8 ohms you got, and that is a
Yeah.
220 volt resistor, right? So when you
Yes.
specify to the NGR vendor, you have to tell 1.8 ohms, 220 volts for 1 minute. Similarly, NGT you have to set dry type, and you have to give this 11 kV bar 220 volts, 19 point or 20 kVA for 1 minute. Okay, so that is how you do the calculation and you determine the ratings. Then you have to make the data sheet, right? Is it clear?
Yes, sir. Clear.
Any doubt?
No, clear.
Okay, this fault current duration, as I told you, are we going to specify any fault current duration here?
No, we will only say that short-term rating, how much time we need.
On what value does the fault current duration depend?
Fault current duration will depend on how quickly I can clear the fault. And the generator, how much time it takes to decay the fault current, TOD.
See, actually, you are going to clear the fault immediately.
Yeah.
Okay, but main it depends on the TDO double dash.
Yes, the time generator takes to
What is TDO double dash?
the time constant it takes for
Open
the
circuit,
fault current.
open circuit time constant, and you are
Yeah.
correct. It is the time taken for the generator this one to decay.
Yeah.
Now, this is one more example. Now let us do this example. You take the voltage as 13.8 kV. say frequency you take 50 hertz,
Yes.
take the power rating as 130 megawatt, take the
One.
capacitance value as 0.45 microfarad. Now you tell me, you calculate one by one and tell me. As you calculate, you tell me.
XC, I'm getting 7077.
Okay. RN,
RM, I'm getting 2359.
okay. Next, what is the NGT primary voltage you are fixing? Here, no, you take directly line to line. You just do directly. You can take line to line only.
99, 13.8.
See, 13.8 divided by root 3 is how much? 1.732 into 1.3.
10.36 is what I'm getting.
See, V divided by 1.732 into 1.3 will always be less than V, right?
Yes, always.
So approximately I will take V as line to line. So here you take it as
13.
13.8 kV.
Okay.
And secondary NGT and resistor rating you take as 220 volts. And tell me what is the turns ratio?
62.
62 you got. So what is the RN? Your resistance you got as 2357 ohms, no? So now what is the RN value?
Resistance.
Actual RN. Actual value of the resistor, how much you are getting?
R secondary, I'm getting 0.59.
See, you
NG.
got 0.59 ohms, right? When the megawatt
Yes.
increases, the resistance value reduces. And when the resistance value become very less, precision is increasing. Okay, so quality of the material also has to be very good. Because if 0.6 become 0.7 or 0.6 become 0.5, there will be lot of change in the current value. Okay.
Okay. Okay.
If 300 become 301, there is not much change.
Correct.
But if 0.6 become 0.5, there is a lot of change.
So we need very precise equipment.
And so make this observation here: higher the megawatt rating, lower the resistance. And say with the resistance become low, the quality, the positive temperature coefficient, the quality of the material, quality of design and all is very important. Okay. Then how much you got resistive component of the fault current?
I got 3.38.
So you took V phase voltage, right?
The line to line voltage by root 3
Line to line by
divided by
3 divided by the
divided by
primary resistance, which is
yes
2357. So you got 3.378. So what will be the fault current in the winding?
it is 4.78.
Okay. So since when the rating of the generator increases, fault current also is increasing. What is the biggest size of generator now?
Bigger size, sir?
Yeah, in the market available. What is the biggest size of generator?
Not sure, sir.
Any idea?
No, 150 maybe.
Pardon?
150 megawatt.
150 is there, 200 is there, 250 is there, 300 is there, 500 is there, 660 megawatt also is there now.
Oh. Okay.
I think maybe up to 1000 also it is there.
Ah.
Because when the rating of the generator becomes very big, then this power current also increases. Then
So
what
this
is
windmill also has megawatt generators, right, sir?
windmill is actually a wind farm, right?
Yes.
Having a number of wind generator. So each one will be how much? Maximum 1, 2, 5 or some megawatt, number one.
Okay.
So what is your doubt on that?
So now if multiple generators are there, so that case, how will they do the grounding, sir?
Actually, in wind, what they do, they bring all the generator to one particular panel. And wind is actually a induction generator, right?
Yes.
It is not a synchronous this one. It is an induction
Okay.
generator. It is actually a delta winding, right?
Uh-huh. Okay. Okay.
So finally, what they are doing, they are adding a special earthing transformer to derive the neutral artificially.
Okay. Okay.
Actually, in Tamil Nadu, lot of windmills are there.
Yes.
So you have any friend, you ask them for a single line diagram.
Okay.
Particularly, don't see normally they export it, they bring it to 33 kV, then they export it. No, don't ask for that. You ask them from the windmill up to that 33.
Right. Right.
There you will see they are actually having this transformer which is used to derive the neutral artificially. Okay, is it clear?
Yes, sir.
Yeah. So now what is the resistive component? Okay, what is the earth fault current?
Default, I got 4.78.
Okay, now okay, what is the current flowing through your this one secondary, the resistor?
Yeah. 1.
This one. Now I want to know what is the current flowing through that resistor.
212 amps is the in the secondary.
Okay, I want basically the current flowing in the resistor, right? Fine.
Okay.
So 211 amps is flowing.
So secondary voltage we are taking 220, right?
Yeah, secondary voltage is 220. So the current flowing in the primary is 3.37 amps, right? So the current
Yes.
flowing in the resistor is 200 amps, right?
Yeah, 212 amps.
Yeah, so last time I told no the NGR rating here will be less. Actually, that is not correct. Actually, NGR will carry huge current here also.
Carrying 212 amps.
So it is carrying 212 amps. That's not a small value. Now let us
This
see.
is flowing through the NGT, correct?
Oh, this is actually see primary current. See, first you have the NGT.
Right.
NGT primary will carry 3.37 amps. NGT secondary winding will carry
Will
200
carry
amps,
212. Correct. Correct.
and that current will flow through the resistor. What is the resistor? 0.6 ohms, right?
Yes.
So what is I square R? Can you determine what is I square R? 211 square into 0.6.
26712.
40,000.
26712.
40,000 into 0.6. 24,000, huh?
26,000.
26,000. Now,
Hmm.
suppose I take my I square R, you multiply by, it is time is around 10 second, right? But actually this 10 second is not constant. The current is falling down, right?
Yes.
This current, what you saw, 211 amps, will
Will
it be,
die out.
yeah, will it be continuously the same current?
No, no, no. It will come down.
It will come down exponentially. So let us multiply, instead of 10 second, I will multiply by 5 second. So
I square
multiply
T,
this
I
20,
square R in
I square R you multiply by T, multiply 26,000 by 5. So you will get how much?
133. 133,000.
Okay. So that much amount of joules, right?
No.
So it is 133 kilojoules.
Yes, sir.
How much you got?
133.563. 133 kilojoules.
So it is a huge amount of energy, right?
Hmm.
So you can see, you even after I have reduced my fault current, there is still so much amount of energy.
Energy.
And very important thing is this energy is not distributed. It is concentrated over an area.
Resistor.
Like when you are doing the welding, no?
Hmm.
When you do the welding, how in a pointed form you are concentrating the energy in the same way. Okay. That's why the time, this all this is very important. Okay. Okay. Now coming back to what is the NGT short time kVA rating you got now? Voltage 13.8 kV, right? Into
Yes. 212 into 220, right?
okay, 220 volts you can multiply by 211 also. Yeah. How much you got?
46 kVA.
Okay. So my short time rating was 46 kVA, right?
Yes.
Just to get an idea, what will be the uh, actual size of the transformer? Just for your idea, you can divide by 2.5 and check that.
Okay. 18.6. 18.6 kVA.
So approximately a 20, 15 to 20 kVA transformer dry type they will use. Okay, but that is not of concern for you. You only bother about the short time rating. And your NGR should be rated. What is the ohmic value? NGR is how much ohms?
1.034.
How much?
1.03.
No, NGR value, how much you got? This 2357 divided by turns ratio square, right?
Point 0.59.
0.59 ohms. So when you buy the NGR, you have to tell 0.59 ohms, 220 volts. Okay.
Hmm.
Rated to carry 212 amps for 1 minute. And NGT will be how much? 13.8 kV bar, 220 volts, 46.6 kVA for 1 minute.
Yes.
And dry type. Okay.
Hmm.
So that is second example. So what we do is we will